Okay, good evening, everyone, and welcome to the lecture. Thanks very much for coming, and thanks very much to Philippa and Daniel for the kind words. When I was 6 years old, my parents, Juliet and Malcolm, bought the family this, an Atari ST computer. And this computer completely changed my life at the time, as well as opening me up to brilliant video games about bouncing eggs and mysterious worlds. It also let me be creative, for example, through drawing programs like this one, which was pretty state-of-the-art at the time, and music composition software. And for a couple of years, I was happy to just play with and explore this amazing machine. But after a while, a natural question came to me, which is, where does this stuff come from? How are these games created? How are these programs made? So I asked my parents, where does this come from? And they said to me, well, there are these things called programming languages or computer languages, and if you know the language of a computer, you can instruct the computer and it will do your bidding. Well, unfortunately, that's all my parents knew about programming languages. And 30 years on, and despite many attempts of monologues from me on the subject, I don't think they know anything more now about programming languages. So I had to imagine for myself, what are these programming languages? And I'll tell you what I imagined. So I imagined that if you had a particular kind of computer, like the Atari, that there would quite literally be a mapping from the English alphabet, the Roman alphabet, into the alphabet of that computer. So for example, the letter A might map to the symbol nabla, the letter B mapped to this funny circle with a cross through it. I guess I thought this because I'd heard of coding, I'd heard of code, and I imagined that we would need to know the code of a computer to program it. I figured if there was another kind of computer, like the good old Mac Classic, then it would have its own alphabet that you would map your letters into. And I thought programming would probably be like the following. If you wanted a game set on a planet with aliens, you would write in English what you wanted. That was your command. I want a game set on a planet with aliens. Then you would get out your mapping from English letters to these funny symbols. And you might translate all of the A's into nablas and all of the E's into sigmas, for instance. And you would keep doing this. It would be quite tedious, but very routine. And eventually you'd have this fully translated command. I also knew from the credits of computer games that humans did the artwork. So I figured there would have to be some kind of mixer where you'd put your translated command and your piece of artwork, you'd feed it through, and it would become your software. So this is my vision of programming. So for the computer scientists in the audience, wouldn't it be amazing if programming was as easy as this? If you had multiple computers, that would be no problem at all. You just have to learn their alphabets. So if you wanted your game set on a planet with aliens to run on your Atari, you would know its alphabet, you'd do the translation. If you wanted to run on your Mac Classic, you would know its alphabet, you'd do the translation, you'd feed these both through the mixers, and out would come your 2 bits of software that would run perfectly on these 2 different machines. This is the dream of what we computer scientists call portability. So from a very young age, without knowing it, I had a dream of portable programming. Okay, the next thing that I was interested in was performance of software. So I soon realized that my illusion of how easy it was to program computers was flawed. And I vividly remember the first program I ever saw that my cousin Gaia showed to me on a very old machine. And I'm going to reproduce that program for you now in Microsoft's Small Basic. So what the program does is it says on the screen, what is your name? And then it reads from the keyboard whatever you type in and puts that in a variable called name. And then it loops forever. And what it does is it says hello and then the name you entered. And then it goes back to the beginning of the loop. And this delay here is a delay for a couple of milliseconds so that you can actually see what the program outputs. Otherwise, it would be too fast for you to see. So let me run this program. It will say to me, what is your name? Alastair. OK, wait for it. Hello, Alastair, 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 hello, Alastair. I remember my cousin showing this to me and thinking, how is it possible that this could be happening so quickly? How could anything possibly work this fast? So as well as portability, from an early age, I guess I was interested in the performance of software. Then the other property that my brothers and I knew about was reliability, because our Atari games would bomb. This would mean that some bombs would appear on the screen and the machine would cease to function. When I was researching this lecture, I discovered that actually the number of bombs indicated what had gone wrong in the program. So for example, a division by 0, which is a very common program error, would be 5 bombs. This is a lovely use of unary representation to give feedback to programmers. Well, we didn't know that at the time. We just knew that the software wasn't working properly. So the 3 aspects of software I knew about without realizing it as a kid were performance, reliability, and portability. And 30 years on, it's these 3 aspects of software that govern my research today. And I would go further and say that anyone working in the field of programming languages is interested in some trade-off between these 3 properties of software. We're all working on methods either to make software faster or to try and make it more reliable, maybe at the expense of performance, or to try and come up with a trade-off that lets us get all 3 of these things. OK, So when I was preparing this lecture, I started to realize I was personifying these properties. I imagined performance being like a cheetah who just wants to go as fast as possible with no regard for reliability, no regard for portability. She's willing to pull all kinds of nasty tricks in the software to make it run fast on a particular platform, regardless of whether that means breaking rules of the programming language. On the other hand, reliability is more like a sloth who's willing to take things nice and slowly and cling on to the branch of reliability and doesn't mind if things go slowly as long as they work, okay? And the sloth and the cheetah, they don't really like each other because the cheetah just says to the sloth, you're slowing me down, I don't need you. If I do things properly, they won't work fast. And the sloth says to the cheetah, you're killing me. I can't reason about your programs. They're too nasty, they're too low level, they're too detailed, okay? And then portability is like this really annoying octopus at the side who says, here's an iPhone, here's a Surface, here's a laptop, here's a GPU. Make it run efficiently on all of them. Make it run reliably on all of them. And well, the sloth and the cheetah, they just don't speak to the octopus because it's tough enough to make software run well, reliably on one platform or with high performance on one platform, let alone getting it running on all of this diverse array of platforms. Okay, so my research agenda is all about trying to develop techniques that software developers can use to improve the reliability and portability of their software, and in particular in support of getting high performance from that software. Hence the title of my lecture, How to Go Really Fast, that's performance, without crashing, that's reliability. I'm sorry, I couldn't find a way to get portability into the title as well. I did think quite hard about it, but I couldn't come up with something. Okay, and in particular, I'm interested in what's called parallel computing or many-core computing. So I just want to spend a few minutes giving you a brief introduction to many-core computing. Let's imagine that we want to process some data. And for the sake of being concrete, let's imagine that the data we want to process is the face of esteemed Professor Daniel Kroning from the University of Oxford. Okay, and what we want to do, this is Daniel's consultancy photograph, and we're thinking of hiring Daniel as a consultant. So we want to know, is he trustworthy? Well, you might know that there's some really tasteful machine learning research on using machine learning to automatically estimate how trustworthy people are. So let's imagine we're going to use this very ethically sound research to judge Daniel. So we're going to compute a result. And if you do facial recognition, one of the first processes in that is called edge detection. So let's say we want to do edge detection on this image of Daniel. And if we run edge detection, we'll get something like this, which picks out the edges of the image of Daniel. For example, you can see the stripes on his tie have been picked out as edges. Obviously, that means he is respectable. So if we do edge detection with just one processor, one core, this would mean that there's a program running on that core. That program's called a thread. Then this will work, but it might be quite time-consuming. And maybe we need to really quickly know how trustworthy Daniel is. So what we might do instead is take Daniel, and I'm sorry about this, Daniel, we're going to cut you up into lots of pieces, okay? And if we've got lots of processors at our disposal, lots of processor cores, then we can feed these pieces of Daniel through the processor cores simultaneously and independently, and we can run edge detection on all these pieces of Daniel in parallel. Then we can put the edge-detected pieces back together to get this edge-detected image, and potentially do this many times faster than we could if we just use one processor core. So that's the basic idea of many-core programming. Okay, and what I want to do now is convince you why you should care about many-core programming, because it may soon be the enabler for a technology that may change all of our lives and that we would like to be reliable. And that technology is autonomous driving. If you read the technology press, you may have heard a lot of buzz about self-driving cars or autonomous vehicles. And you may also know that it's already possible to buy a simple form of autonomous vehicle, namely a vacuum cleaner that automatically roams around your house, hoovering up your mess while you're out. So whether it's a car or a vacuum cleaner, let me just call them both a vehicle, this device is going to be powered by computer vision technology. It will be equipped with one or more cameras. Those cameras will take in the surroundings, and the robot, the vehicle, will use the camera feed to make decisions, for example, to determine where it is, or to determine what action it should perform next, or where it should move to. Okay? And we're very lucky at Imperial because we've got one of the world's leading computer vision and robotics groups, and we host the Dyson Robotics Laboratory, headed by my colleagues Andy Davison and Stefan Lutneger, who I'm delighted have been able to come along to the lecture tonight. And I'm going to give you a demo of some technology that they have been working on, which is called elastic fusion. Is it looking good, Andrew? Yeah? Okay, so for this demo, I need a couple of volunteers. So I would like to pick on Daniel again. Can you come up to the stage, please, Daniel? And I would also like to pick on Muffy Calder. Can you come up to the stage, please, Muffy? I wonder if you could sit down in these chairs. So the demo I'm going to show you relies on this piece of equipment called a depth vision camera. And what this camera does is it takes in not only color information, but also depth information about how near or far objects are. And the elastic fusion demo is going to use this camera to build up a really detailed 3D model of whatever I pointed at. Okay, Andre, let's go. Oh, we need to switch, sorry. Can we switch to HDMI 1, please?
All right.
OK. So you need to keep still, by the way. So I'm running the demo, and what you can see is that we've got a picture of Muffy and Daniel, and the picture is being populated. Oh, my hand is shaking. It didn't shake during the practices. The scene has got a whole load of these things called circles that are being used to build up a very detailed 3D model of my participants. I'm just going to make the 3D model a little bit more detailed by going a little bit behind Daniel.
Can we look yet?
You can't look yet, no. No. OK, and a bit over the top. OK, Andrew, I think that will do. Do you want to pause the demo? So you guys can relax now, and you can have a quick look at the screen. I'll need you for a bit longer, but you can relax. So now Andre's going to navigate around this demo, and what you can see is it really is a rigid 3D model of the scene. Let's maybe go around to the front of them, Andre. And what you can see here is that it's not just a video of Daniel and Muffy. You've captured really what they look like in immense detail using this 3D model. All right? So technology akin to this is going to be inside these autonomous vehicles that's going to be used to get a very accurate three-dimensional model of what you point them at. Now, the reason this demo works is that we brought along this extremely heavy machine from Imperial that's got inside it a many-core processor, a massively parallel GPU that's got literally thousands of parallel processing elements. And it's only because of the parallelism inside this machine that this demo works. And to illustrate that, I want to run the demo again. And this time, we're only going to use 1/8 of the parallel processing capabilities inside this machine. So if we kick off the demo, then what we should see is that it does work. It just works very, very slowly. So we're building up this view of Muffy and Daniel. Okay, and it's actually a little bit less accurate because the data is not being processed at a high enough rate. Right? But if we are careful, if we move the camera slowly, we will get an accurate 3D model being built up. It would just be built up much slower than we would like. Okay? So you might ask, does this matter? Well, it does matter if this kind of technology is being used to make decisions in an autonomous vehicle. If you've got a fast algorithm that can make a decision quickly, but inaccurately, you might prefer that to a very accurate, slow algorithm that's going to decide whether to put the brakes on if a pedestrian's in the road, because if it runs very slowly, that might not work out very well for the pedestrian. OK, do you want to kill the demo, Andrew? So you're going to just have to sit tight for a little bit longer while I show the audience some code. So what Andrew's going to show now is some of the source code behind this demo. This code is written in a programming language called CUDA that comes from NVIDIA. This is the programming language you use to target NVIDIA GPUs, graphics processing units, and we have one of these inside this machine. And I don't want you to look at the code in any detail. I just want you to observe a couple of things. First of all, this code is CUDA code that's specific to NVIDIA GPUs. So what property does this code lack? Portability. This code isn't portable. This code will only work on NVIDIA GPUs. If we want to run it on a different parallel accelerator, we'll need to work hard to rewrite the code. The other thing I want you to notice is that the code is pretty detailed. It includes close-to-the-metal constructs that squeeze the last ounce of performance from these NVIDIA GPUs, and it can be hard to use those programming constructs correctly. And Andrew is now going to go to a particular line of the program that's got what's called a barrier operation, this line that says sync threads. This has got a barrier synchronization. And what sync threads does, a barrier, what it does is it causes every thread running the program to wait until all the threads get to this point of the program. Okay? And after all the threads have reached this program point, they can carry on processing. You use a barrier if phase 2 of a computation depends on phase 1. Phase 1 can be done fully parallel, but phase 2 depends on the results of phase 1, so we need to wait until everyone got to the end of phase 1 before we proceed with phase 2. To give you an everyday example, think of a general election in the UK. We're going to elect the next prime minister. Well, voting is a massively parallel process. Voting can go on at polling stations all around the country in parallel. And then when voting closes, we take all of the ballot boxes in a constituency to a voting centre where they're counted, and at the end of the night, that constituency can declare its seat. But we've got to wait for all the ballot boxes to arrive, and we've got to count them all before we can make a final decision. So that's like a barrier. We have to wait until everything is ready. And then we have another barrier. We have to wait until we declare who's prime minister. We have to wait until all the constituencies have been counted, and only then can we decide who's prime minister. If, for example, we don't get the votes from Scotland, then we're likely to get a Tory landslide victory, for example, where we might have got a completely different result if we'd included Scotland, and maybe a result that would be better for the country. Well, I'll leave you to decide on that. So barrier synchronizations are really important, and Andrea is now going to remove this barrier synchronization from the program, and we're going to run this demo again, and now we're going to see what happens. And you can relax soon, okay? This is your last engagement. Well, not yours, Muffy. You've got to give the vote of thanks. Okay, so everything seems to be sort of working okay, or does it? So the scene is kind of appearing, but if I move the camera around a bit, what we should see is that things are going to go kind of horribly wrong. My hand isn't shaking that much, first of all. And if I move the camera around and try and get another view of Daniel, can we get another view of Daniel? No? Okay, let's get another view of Daniel. Okay, here's Daniel and Muffy again. Let me move the camera around a little bit. Oh, there's Muffy again. And we've got Muffy here again. And now, let's just wait a minute. And oh, look, there's another Daniel. And Muffy seems to sort of have two heads. And now if we pause the demo, we can navigate this 3D scene. And it's like a 3D scene from hell. This is a 3D scene where you wouldn't want to live, right? But it would really have been better if the application hadn't run at all, if removing that barrier had caused the program to crash. If the program had crashed, there's no way we could possibly have thought that the behavior was acceptable. But what actually happened is the demo seemed to work all right at first, and only after a while did things go bad. And if this bug was not as obvious as this, if it was more subtle, then a problem like this might end up making it through into some production software, and maybe the bug could actually manifest in quite catastrophic ways in other scenarios that weren't used during testing. So bugs in these parallel programs due to missing synchronization can have catastrophic consequences, but they can be hard to detect during testing. Okay, let's thank Muffy and Daniel for their participation. And Andrew to help me run it. And if we could go back to HDMI 2, please. Okay, so can you please raise your hand if you've ever written GPU code? Quite a number of you, which I'm glad to see. Can you raise your hand if you've ever booked something online? Okay, good, all of you. So I want to just give you a bit more of an intuition into what makes parallel and concurrent programming hard by explaining how a concurrency bug caused trouble for my wife, Christine. My wife, Christine, runs a business called Little Wild Things in Charlbury, where we live, who specialize in outdoor nature play for preschool children. And one of the things that Little Wild Things offer are sessions where parents can bring their children to a patch of woodland to engage in these outdoor activities, and parents have to book in advance. One evening, Chris put 20 places online using a third-party booking system that Little Wild Things had been using since their inception. And initially, no places were booked, 20 were available. After 5 minutes, she said to me, Ali, 12 spaces have gone in 5 minutes. And we were celebrating because this was good. The company was, the reputation was growing. We had some dinner, and then at 8:30, 23 of the 20 places had gone, and -3 of them were available. So what went wrong? Well, I don't know what went wrong because I don't know the code behind the booking system. But I imagine it might have been something like the following, that the booking system would say, when a parent would try and book a place, it would ask, is a space available? If a space is available, it would take a payment from the parent. And if the payment succeeded, the space would get reserved for the parent. Okay? Well, why might this be a problem? Let's imagine it's 8:25 p.m. 19 of the spaces have been booked. 1 space remains available. A parent logs on and says, I want a space. And the system says, good, there's a space available, you can have one. Please pay me. So now the parent gets their credit card out and starts fumbling with their number and can't remember their PayPal password or whatever. And in the meantime, a bunch more parents come on and ask, is there a space available? Well, the system doesn't actually reserve the space until after you've paid. So as far as the system is concerned, yes, there is still a space available. Finally, parent 1 finishes paying, and this space goes. So now we have 20 spaces booked and 0 available. But the trouble is the other parents have already got past the checking of availability and have been promised a space. And one by one, as they finish paying, the system gives them away spaces, and we end up with 23 spaces booked, -3 available, and Chris has to start sending apologetic emails to parents explaining they can't come after all because the adult-to-child ratio won't be good enough in the woods. Okay, so how do we fix the problem? Well, the issue seems to be to do with the fact that we check whether there's a space available, and then a lot of time elapses before we reserve the space. So maybe we should immediately reserve the space after its availability has been checked. We could fix the system by saying, if a space is available, reserve it, okay, and then take payment. All right? We'd have to resolve the issue of what to do if the payment was declined, but let's forget about that for here. Well, the trouble is that it's possible, in that case, much less likely, but still possible, that 2 parents will log on almost simultaneously, and the system will still say, yes, there's a space available for both of them. Then the first space will be reserved, the second space will be reserved, and the parents will proceed to pay. It will end up with -1 space available. So actually, this doesn't fix the problem. If we really want to fix the problem, we need to use another kind of synchronization called a lock. So what we need to do is say, when you book a space, first of all, the system locks the bookings so that no one else can access the bookings for the time being. It will check, is there a space available? And if so, it will reserve the space. And the lock means that those 2 things are not divisible anymore. They can't be done separately. Then the lock gets released, and if a space was reserved, then payment will be taken. And if we do this, it fixes the problem, right? Because it forbids the possibility that two parents are simultaneously in the process of asking for a space and having the space reserved. We can have them happen in this order or that order, but they can't overlap. Okay? So I've shown you two kinds of synchronization. Barriers, where everyone's got to get to the same point, and locks, where a thread takes exclusive access on something like the booking system. And these are used to eliminate bugs in concurrent programs, and the issue is that insufficient synchronization can lead to bugs. But the problem is that bugs can be really hard to find because the number of behaviors in these systems can be astronomically large. So I now have a challenge for any mathematicians in the audience. Let's say we've got 23 parents, and there are 3 actions that they can perform. So there's the action of checking availability, taking a payment, and reserving a space. So let's imagine we've not fixed the system yet. Let's also imagine these have got to be performed by a single parent in this order. And let's also imagine that there are plenty of spaces available. The spaces won't run out. So how many possible ways can we have 23 parents perform these 3 actions such that the actions are ordered inside a given parent's sequence, but the order between different parents doesn't matter? So I'll give you 30 seconds. Anyone like to shout it? I'll sit down here for a minute. Okay. Stick your hand up if you want to venture a guess. Come on, it's the Royal Society. You need to show off. Okay, well, I'll tell you. I had trouble working this. I had to actually get my colleague Maddie to help me work out the answer. It's actually pretty simple, but I'm not very good at this kind of thing. Okay, so if we didn't care about the order, green, white, red, then there would be 23 times 3 factorial ways we could permute the 69 events that would occur if we have 23 parents that could do 3 events. Right? The trouble is that a given parent's got to do green, then white, then red. So we need to divide this number by 3 factorial, which is the number of ways that a parent's events could be permuted, to the power of 23, because there were 23 parents. And the number is this, which is a really big number. That's larger than 10 to the power 80. And if 10 to the power 80 doesn't mean anything to you, the estimated number of nanoseconds since the Big Bang is less than 10 to the power 27. And 10 to the power 80 is much, 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 much bigger than 10 to the power 27. Okay, so it can be very hard to find problems in these concurrent systems because of this explosion of behaviors. So now let me start to tell you about my research contributions. We want to attack these many core systems, and one question we'd like to ask is, given these programs that are executed by really a very large number of threads, can we analyze them? Can we find bugs in them, despite this behavioral explosion that I just alluded to? And the first project I want to tell you about in some detail is called GPU Verify. It's a way of formally verifying certain properties of GPU kernels. And I did this in collaboration with several colleagues, but from my research group, this was done with Nathan, Jeroen, Adam, Ethel, and Peter. So the idea of GPU Verify is we give it a piece of GPU code that's written either in CUDA, which is the language we saw a bit earlier in the demo, or OpenGL, which is an open programming model that's a bit like CUDA. And what it does is it thinks for a while, and it tells us either that the program is well synchronized, that means barriers have been used appropriately in the program, or it says that there's a possible synchronization bug, a case where you may have misused a barrier or omitted a barrier where a barrier was needed. The goal here is to help programmers who are writing code in these languages to develop reliable code, and the big challenge is how we cope with this behavioral explosion because of all the threads running the GPU program. Okay, so imagine that we've got a sequence of barriers, and between these barriers, there are going to be threads running in parallel. I'm going to use this parallel bars to indicate that threads are running in parallel. And I'm going to show you 8 threads running in parallel here, but really there will be thousands of these threads running the kernel. So the point of a barrier is it lets threads send messages to each other. Thread 1 is allowed to send a message to thread 2 as long as there's a barrier in the way, because the barrier ensures that any data thread 1 wrote before the barrier will be ready for thread 2 to read after the barrier. Think again about the general election. Okay? Once we get all the votes at a polling station, we can declare the candidate, and then when we're deciding who's prime minister, we know the candidate for each constituency. What's not allowed is for a thread to send a message to another thread in between the barrier. To use the general election example, it's not okay to say, of course people speculate all the time, but we can't say absolutely that this candidate has won in this constituency until we've counted all the votes. We can't say this midway through the vote counting. All right, so what GPU Verify is trying to do is to find examples of this and flag them up and say, look, you need to fix this, or to prove that there can be no such examples and show that all communication has this nice form here where there's a barrier in between. So the problem is that we've got loads and loads and loads of these threads running in parallel, and when many things can happen in parallel, we get this explosion of behaviors. So the first trick we pull in GPU Verify is that we chuck away this parallelism. We say, let's forget about the parallelism and pretend that the threads are running sequentially. Just to clarify, I'm not saying that we want to really change the program and make it run sequentially. That would kill all of the performance we're getting. But what we want to do, just for the purposes of analysis, is pretend that the threads run in this fixed order. But what we're also going to do is instrument the code to check whether they would have tried to communicate if they were running in parallel. All right? So we're going to run them in sequence, but we're going to check whether if we'd run them in parallel, they would have communicated. And this doesn't miss any synchronization bugs, because there are two cases. There's one case where the threads don't communicate. If they don't communicate, then it doesn't matter which order they executed, because they can't influence each other. The state of the program at this barrier will depend only on the state of the program at this barrier, because the threads are going to run without talking to each other and get to the next barrier, so they can't influence each other. If they do influence each other, that means they've tried to communicate, and that's not allowed, and we are going to detect it through this checking for attempted communication that I'm not going to be able to go into the details of here. So either way, we're going to be okay. We're going to find there's a problem, or there is no problem, and then this order is just as good as any other order we would have chosen. Okay, so this is great because we're in the world of sequential program reasoning, and we've got loads of research on how to reason about sequential programs, dating back to the work of Tony Hoare, for example. So that's a much better place to be, but the trouble is it's a really large sequential program. We don't really have 8 threads, we've got thousands of threads, so we would have a program that would be thousands of times longer than a normal program, and that would be very hard to reason about. So the next trick we pull is we say, well, let's not reason about all the threads, let's just reason about 2 threads, okay? But we're not going to reason about 2 specific threads. We're not going to reason about, for instance, threads 5 and 12. We're going to reason about 2 arbitrary threads, threads I and J. And we're not going to assume anything about these threads other than they're not the same thread. To make this work, we also have to pretend these threads are running in a hostile environment that over-approximates what the other threads might have done. And this still doesn't miss any synchronization bugs, because I and J are arbitrary. If we manage to prove that this program, run by 2 arbitrary threads, is free from communication errors, that means that no matter which I and J we pick, the program is free from communication errors. So if you're worried about threads 5 and 12 communicating, well, if we prove that this program is free from communication errors, that shows that no threads can communicate, and that includes threads 5 and 12, or any other choices of I and J I would have made. And this hostile environment takes account of the fact that the program isn't really run by 2 threads, it's actually run by many more threads. And the price we pay for that is that the hostile environment makes the analysis imprecise, and sometimes GPU Verify will tell you it thinks there's something wrong with your program where there isn't actually anything wrong at all. That's what we call a false alarm. So that's the price we pay for collapsing down to this simple to analyze program. So what GPU Verify does then is it takes this original program, run by thousands of threads, collapses it down to this 2-thread program, and feeds this into a reasoning engine, and the reasoning engine makes the final decision on correctness. And the reasoning engine is built from 2 components that came from Microsoft Research: Boogie, which is a verification tool, and Z3, which is a theorem prover. And the collapsing down to 2 threads piggybacks on top of a compiler framework called Clang that's been contributed. It was started by Apple, and it's been contributed to by many other companies, including Google. And it's really great that these big companies like Microsoft and Apple and Google, who maybe we think of in general as being secretive companies, actually they've contributed an enormous amount to research. There's no way we could have made GPU Verify work on realistic programs if we'd had to build all of this by ourselves. We were able to piggyback on these really amazing projects from industrial partners, contributed also to by many academics, and that made us be able to do bigger things with this project than we would have been able to do otherwise. And thanks to the CARP European project that I coordinated, we were able to work together with ARM, who are a UK-based company who are very well known for designing CPUs, but also have their Mali line of GPUs. And Anton Lokmatov, who is a long-term collaborator of mine who was involved in this project, he worked with ARM to get GPU Verify integrated into the Mali graphics debugger. So if you're a Mali programmer, you can use GPU Verify to help debug your code. Okay, we've also been doing a bunch more work that I don't have time to tell you about related to analyzing programs. My student Chris is doing some really exciting work on analyzing concurrent programs using a method called systematic concurrency testing that my former students Paul and Pantazis have also worked a lot on. And my PhD student Dan is working on symbolic testing, and my new student David is working on property-based testing, which are both very exciting ways of testing programs, although Dan and David are actually working on sequential programs, so don't tell anyone that. But no, seriously, sequential programs are still extremely important, arguably more important than parallel programs, because there's more sequential code in the world, so we're also interested in that in the group. It's not just multicore. Okay, next up, if we're going to write programs in these languages like CUDA and OpenCL and run them on devices, it's important that we understand something about how these languages work and these devices work, what behaviors the languages allow, what behaviors the devices allow. And we've also been working on this. For example, John Wickerson, a former postdoc of mine, and Tyler Sorensen, who's just coming to the end of his PhD, have worked on memory models for the OpenCL programming language and for GPUs. And Tyler, Hugh, and I have worked together on a method for making GPU programming more portable that I'll say a few words about in a minute. And my PhD student, Dan Yorga, and Tyler and myself have been working on looking at multi-core interference between different components in a multi-core system. So I don't have much time to tell you about these works, but I just want to say a few words about two of the papers here that I'm the most proud to have been involved in. This is a paper led by John Wickerson, who's now an independent research fellow at Imperial. And it's about a collaboration we did with AMD, Advanced Micro Devices, who are one of the other main GPU vendors. And we worked with AMD to use mathematics to formalize an extension to the OpenCL programming model and some next-generation GPU support for that extension. And what we found is that actually the next-generation GPU support had some subtle defects in it that AMD were able to fix years before they would have fabricated this processor, potentially saving a lot of money. The other paper was led by Tyler Sorensen, and it's about cooperative kernels, which is a new programming language extension we've proposed for OpenCL that should make it possible to write so-called blocking algorithms that require fair scheduling between threads to make them run portably on GPU systems. Okay, let's imagine you've written a many-core program, and you want it to run on some many-core devices, some GPUs. What you need is what's called a compiler that will take the many-core program and translate it into device-specific assembly code to run on the device you care about. The compiler is like a much, much, much more sophisticated version of the alphabetical mapping I imagined when I was a kid. Maybe you've gone to great efforts and you've actually used GPU verify to analyze your many-core program to check that it really is free from synchronization bugs, or you use various other techniques that can be used to analyze programs at that level. So then what question should you ask yourself? Very good. Do I trust my compiler? Okay, what if there's a bug in the compiler? We've reasoned about this program, but it's been compiled into some low-level code that's invalid. It doesn't actually respect the meaning of the original program. In particular, for what it's worth, that would invalidate any guarantee a tool like GPU verify had given you, because GPU verify has reasoned about the source program, not the target program. So the situation is worse if you've actually written your code in a high-level domain-specific language, like the Pony programming language from my colleagues Sophia and Sylvan at Imperial, or the C# language that we've worked on together with Pantazis, or various other high-level programming models that you want to translate down into lower-level representations. There could be bugs in these compilers too. So as a little aside, I'm going to tell you in a moment about a technique called graphics fuzz that started with an MEng project from my student Christopher Libri, where he worked on a tool called CLSmith for finding bugs in OpenCL compilers. And since then, Andre, Hugh, Paul, and myself have piled in and worked on techniques for finding bugs in various kinds of compilers. I'm going to show you a little demo of that in a moment. But I want to ask, hands up if you primarily use the Google Chrome web browser. Okay, so probably about half of you, which seems about right. It's apparently the most popular web browser in the world at the moment. So what I'm going to do is switch into a different tab. I'm going to show you Google Chrome. Now, this program here, which again I don't really want you to read, this is written in the OpenGL shading language, and all you need to know is it's responsible for this pretty picture drawn in the background. This has got a graphics shader. So what I'm going to do is I'm going to write in this program a little loop. It's going to say for int m equals 0, while m is less than 1, increase m by 1. So this is a loop that goes around once. So this piece of code, if we put it inside the loop, is going to get executed once. But it was already going to be executed once, right? So hands up if you think the program's behavior should stay the same when I inject this code. Okay? Not that, oh. Okay, good number of programmers in the audience. Okay, so let's remove the statement. So this compiles on the fly, so it's compiled and run. So good, the program behavior has been preserved. Okay, who uses Microsoft Edge? 1, 2. You have to, Andy, right? You have to. You have to use Bing as well, don't you? Okay, so let's go to Edge, and let's write this line of code. Bam, okay? we've written this line of code that does the loop once, which was what it did anyway. If we don't have the code, we get the pretty picture. With the code, we get this wrong code. Okay? So this illustrates a bug in Microsoft's compiler that targets the Intel GPU in my Surface here that I'm running this from. But I just want to emphasize I picked on Microsoft simply because it was really easy for me to demo that bug. We found very severe bugs affecting iPhones and Galaxy phones and all kinds of other devices. So there's nothing particularly wrong with Microsoft's compiler compared with other compilers. All right. So I want to tell you how we find these bugs. If you've got an OpenGL program, which is one of these graphic shader programs, and you want to run it on a device, you push it through a GPU compiler. You then run it on the device, and an image gets rendered. What we do in our work is we take the original program, and we apply a whole lot of transformations to it to get a stack of these transformed programs. The transformed programs are, by careful construction, guaranteed to have the same behaviors as the original program. We apply transformations, like wrapping something in a one-iteration loop, that shouldn't introduce any more behavior. They should only preserve behaviors. If we push those programs through the compiler and run the resulting code on the GPU, we should get a stack of images that are the same as the original. And if we get a bad image, we know there's a bug in the compiler. Okay? And it's via that process that we found this bug in the Edge compiler, for example, and we found many bugs in other platforms. And interestingly, we found that GPU compiler bugs pose a security threat. This is something we didn't plan to try and show with our work, but it came out of the wash. So this is an image of a web page being viewed on a Samsung Galaxy S6 phone. We're looking at the Bank of America homepage here. And what we found is that we could exploit one of these compiler bugs to construct another web page so that if you switch to that web page, what it's meant to do is render some graphics. But what it does instead is it renders stuff from your Bank of America tab. So it renders, I think you can see here that we've got the kind of banking and bank of am. So this has been scrambled up, but nevertheless, it's been rendered. And what's more, this can be captured and sent off to a remote server for processing. So these graphics compiler bugs can be quite security relevant. And we found a bug affecting the iPhone that Apple were kind enough to acknowledge us for in a recent iOS update, and an NVIDIA security bug that, again, NVIDIA were kind enough to acknowledge us for in a recent security bulletin. So what we're doing now, given that this work has been reasonably successful, or it's fairly automatic, we're going to try our luck with a spin-out company called Fuzz, whose goal is to try and protect end users and developers from GPU-related bugs. And the idea of Fuzz is as follows. Currently, we've got a situation where there are multiple GPU companies that produce what are called drivers that run inside devices. So those drivers are developed by these companies, and they have some kind of quality assurance process to try and make them reliable. The drivers go into consumer devices like smartphones, laptops, anything with a screen, really. And the trouble is that if there are bugs in these GPU drivers that escape the quality assurance processes, they make it through into the consumer devices, and then end users can see the impact of that through problems like the one I alluded to affecting the Samsung Galaxy S6 phone. So what we want to first do with Fuzz is make it become the gold standard for testing the device drivers in consumer devices, to identify bugs in those devices so that the vendors can be made aware of them and can fix them, and those fixes can then propagate into these consumer devices so that end users don't suffer anymore. But we'd like to go much further. We'd actually like to make Fuzz be embedded inside these companies to augment or maybe replace their quality assurance processes so that when driver bugs occur, which is going to happen because driver programming is really difficult, Fuzz can find the bugs, the developers can stamp on the bugs. When they occur again, Fuzz will find them, the developers can stamp on them, and ideally, no more bugs will make it out into consumer devices. Okay? And this mission to use various different techniques to stamp out bugs, I suppose, summarizes my research agenda. So what I'm doing in my reliable many-core programming fellowship from the EPSRC is trying to take techniques at the intersection of programming languages, formal verification, and testing, and apply them all the way up this many-core stack, looking at improving programming language specifications to make them more precise, formally verifying critical components, come up with intensive testing for components that are hard to verify, with the mission of stamping out bugs to a very large extent across this stack. One thing I want to note, though, is that the work I presented to you so far, and all my work so far, really, has assumed that reliability is an absolute concept that can be defined. I'm not saying it's easy to define, but I'm assuming that it can be defined. But let's think about this autonomous driving example again. A bit of an elephant in the room here is that it's really hard to say what it means for a pedestrian detection algorithm, for instance, to be reliable. At what exact moment should it slam on the brakes, given that's dangerous for the driver, and given that it may have incomplete information due to the weather conditions, say? That question doesn't have an answer. We can't say specifically when this event should occur. Imagine a situation where a car has got several options it can make, but all of them are going to lead to someone dying. Maybe there's another car here, a pedestrian there, a barrier here, and if it slams the brakes on the driver, it might get killed. How can we say that that system is reliable? We can't really absolutely say what reliability means. And if reliability becomes a fuzzy concept, then what does portability mean? What does it mean to have something work reliably on multiple platforms if we don't know what reliability means? And then performance gets really interesting because performance and reliability become intertwined in a very tight manner because, once again, we've got the choice maybe between a high-performance pedestrian detection algorithm that will quickly make a decision, but it might be the wrong decision, or a very accurate, slow algorithm that will make a better decision, but too late. So I think for those of us who work in testing, verification, and programming languages, we need to really turn our attention to this very challenging situation where reliability, portability, and performance have become fuzzy and somewhat intertwined, and I'm really excited about taking my research in that direction in the future. Okay, so that takes me to the end of the lecture, and I've got a lot of thank yous I need to make. I'll try and be brief. I want to say a huge thank you to my amazing Multicore programming research group. I'm really glad that very many of you are here tonight. There's no way I would be standing up here delivering the Roger Needham lecture if I hadn't worked with you amazing people. Thank you so much. And I also want to say thank you to my many other co-authors, too many to list here, but it's been a pleasure to work with lots of scientists internationally. Wouldn't be possible to do this research if we didn't get funding, and I've been fortunate enough to receive funding from the UK government, the UK research councils, the European Commission, and a number of companies who've been generous enough to give their money and their support to my research, so thanks to all of them. For this lecture, I had a lot of support from my very dedicated PhD students, Dan and Andre, to get this demo working. It worked! It worked. We practiced it so many times, but it worked. And I had a lot of support also from my wingman, Hugh, and my former wingman, Jeroen, so thanks to you guys. And I want to also thank Andy and Stefan from the Dyson Robotics Laboratory for providing the demo, and Lloyd Kamara from the Computer Support Group at Imperial for technical support. Speaking of Imperial, I've been at Imperial for 6 years now, and I really think of it as my home. It's worth the commute from Oxfordshire to Imperial to be with such brilliant colleagues, to work on exciting topics where there's a wealth of expertise available and a very friendly environment. I want to thank all my colleagues for coming tonight and for being such great people to work with. And I also want to thank my former homes, the University of Glasgow, where I did my degree and PhD, the CodePlay software, where I spent some time as a developer after my PhD, and the University of Oxford, where I spent time as a postdoctoral researcher. Thanks to all of those places. Okay, and now on to some really personal thank yous. My brother, Jerry, has come all the way from Dundee to be at the lecture today, so thank you very much for coming, Jerry, and thanks for being such a good friend to me always. And more than anything, I want to say thank you to my amazing wife, Chris, and our beautiful children, Poppy and Felix, for all their love and support every day, and for putting up with my constant stresses about the many academic deadlines that we have that seem really, really urgent, and there's always another one, and always another one. And this is just, just one more night of staying up and working on this, and they all seem so urgent, but really, in the grand scheme of things, they're not that important. So I want to thank my family for reminding me that there's a lot more to life than computer science. Okay, that takes me to the last slide, and you might just have to read it because I predicted that this would happen, but I'm going to do my best, okay? So I want to dedicate this award and this lecture to my amazing parents, Malcolm and Julia Donaldson, to thank them for, well, you can read it, for supporting me through my whole life, and for 30 years ago doing something really important, getting me this. Thank you.